So today we are learning the step of relational database design, and today we will be learning about the normalization. In gate questions, most of the questions are asked from SQL. I covered few of the questions, but if the time permits, I am going to cover more SQL functions as well. But today I am starting with the relational database design. In this chapter, we will learn what are the features of good relational database design, and we will see the definitions of first normal form. Then we will learn how to calculate the functional dependencies and what is the role of the functional dependency in the normalization. We will also see the four normal form and the multi-value dependencies as well. Now you have to see this schema and tell me whether this schema is a good schema design or not. If it is not, then why it is not? Uh, in this schema, all the employees name, salary, and the employee where it is working in the department building and budget of a department is also added with it. This schema is what can be the problem with this schema is you can see that if you see the computer science and engineering department, this cats is working in the computer science and engineering department. So all these three entries are here related to the department. If another person is also in the computer science department, then the entry is going to be repeated. So if you have 100 students in the computer science department, you have to repeat these entries for 100 number of times. Means it is a waste of storage, as well as it is not a good practice to have the repeated entries into the database. So this database design is not a good database design. Why it is not a good database design? Because the data department is totally an isolated entity than the students. So you can keep the record of a employees or a student in one relation, and the related department, whatever fields we have for the department in the another relation. That will make our system more sensible, as well as it will not force you to have the multiple entries for the same computer science department like this. Sometimes merging of sometimes multiple fields in one relation is not it is not with the repetition of entries. If you see this section, in this section, course id, section id, semester, year, building, and room number, in this we do not have any repeated entries. Everything is fine, so we can go ahead with this table only. But even if you want, you can divide it into the two part, which is a section, class, and section. It is again a good division, and this keeping them together is also a good choice. So because it has no repetition, when the repetition comes, then you have to divide your relation into the multiple relation. Now we have seen in the first slide this relationship, in the first slide, the institute department relationship, it was not a good design. Why it was not a good design? Because the department name was not a candidate key for a table. And department name, and in this relationship, the department tends to building, budget, this functional dependency holds. We will be learning the functional dependency in detail, but whenever some functional dependencies holds for a particular table, the left hand side of the functional dependency should be a key. Then only that relationship will lead to a good design. Because department name, that is left hand side of functional dependency, is not a key. You can see that this department name is not a key. You are finding the multiple entries. If it is not a key, means this relationship is not a good design. Uh, what is the good design for it? The good design for it will be, you can keep ID, name, and salary and department name in one table, and in another table you can keep department name, building, and budget. So in the first table, you will have 4 field: ID, name, salary, and department name. Department name is required because how do you identify in which department you are? In the second table, you can have the field department name, building, and budget. That is a good division of a relation schema into the two schemas. But every time, every decomposition is not meaningful. If you see this, in this ID, name, street, city, and salary, and you have decomposed into ID, name, and the second decomposition is name, street, city, and salary. This decomposition is not a good decomposition. Why it is not a good decomposition? Look at this. In this table, we have these 5 fields, and you have decomposed it into 2 tables. One table consists of ID and name, and the second table consists of name, street, city, and salary. This decomposition is not a good decomposition because whenever you are combining these two decomposition, how will you be combining with these two decomposition? You will be combining with using the natural join or natural join. So if you combine it by using the natural join, you can see that this first kim will be joined with these two kim, and the second kim in the table 1 will be joined with these two came in the second table. So if you combine these two tables, you are generating the 4 entries of Kim, but in original table it was only 2 entries. How the 2 entries have become the 4 entries? Means you lost some information. You are generating the rows which are not in the original table. So if this decomposition is correct, you should get the original data while you are combining the decomposed table. But in this case, if you are combining this decomposed table, you are not getting the original data, means you are losing some information. Instead of 2, you are getting 4 rows. So it is not a, it is a lossy. You can say that it is a lossy decomposition. You are losing something. Now you have to check how the decomposition is lossless. Lossless means no loss of information. How do you say the decomposition is lossless? Say for example, you have a relation R. In this relation, you have 3 fields A, B, C. Now you have decomposed it into 2 tables. While you are decomposing a relation into 2 relation, one field should be common. If you do not keep any field common, you will not be able to join them. So one field should be common in both of the tables. So we have divided it into two tables. One is AB and second is BC. AB and BC. Now you have to check whether this decomposition is a lossy or lossless. To check it, if you combine these two tables, means it will be combined on field B. One entry will be combined with 1, 2 entry will be combined with 2. So in finally in the table you will get these 3 columns and these 2 rows. You can check that after combination you are getting the original data, means it is a lossless decomposition. Now if you have been given such type of decomposition, how do you check whether it is lossy or lossless? In GATE these questions are asked, so you need to understand it very well, which decompositions are lossy and which decompositions are lossless. If you calculate the decomposition lossy or lossless, you have to first find out what are the common fields. Means you have to calculate the common attribute R1 intersection R2. In this case, the common field is B. So first you calculate R1 intersection R2. So if you calculate the R1 intersection R2, which is B in our case, from that B, you should have the functional dependency to either relation R1 or relation R2. What does this mean? Common field B should have B, functional dependency B, the functional dependency of B, the common field is B. B, which is should be in the left hand side, it should have functional dependency on either AB. AB is relation R1 or BC or BC. B is functionally dependent on either AB or BC. If any of them is true, then our decomposition is lossless. So how to check whether the decomposition is lossless or not? You have to first find the common field between the decomposition. That common field between the decomposition, its functional dependency, B tends to relation either relation R1 or relation R2 holds. What is relation R1? Relation R1 is AB. And what is relation R2? The relation R2 is BC. So any of one of them should hold, then only this relationship is lossless. So this we have to first check the attribute of you have to first find out the union R1 union R2. It should give you all the attributes of R. R1 union R2 is R1 is AB and union BC. Union should give A comma B comma C. So the first condition should hold. Second condition is in R1 intersection R2 it should not be the null. In this case we have B. It should not be the null. And whatever is there in the R1 intersection R2 it should have a functional dependency either on R1 or on R2. So these three conditions hold, then your decomposition is lossless. Now we will see the normalization and the first normal form. In the normalization, we are going to give the good design. We are going to decompose in such a way that your database design is good. We will see the definition of good design as well. But before it, we are learning the first normal form. The first normal form says that your domain is atomic. The domain is atomic means whatever entries you are filling in a table, that entry should come from a domain, say for example id, name, class number, should come from the domain which has the atomic entries. Atomic means that value cannot be further subdivided. If I have my enrollment number, I am not going to divide into the parts to get the different parts of enrollment number. The entry means only one entry will be considered and I will always treat it as a one, retrieve it as a one, insert it as a one, delete it as a one. I am not going to divide it. Single entry means one entity. That is the atomicity. So every entry is an atom that cannot be further subdivided. So it is coming from the atomic domain. So if in a table, if in a table you have all the entries which are atomic, then this table is in first normal form. Generally, all the entries, all the tables are in first normal form. When this table cannot be the first normal form, say for example, in this you have been given a roll number like this, and now you want me to find out if the first two codes are giving me the branch and the second last four codes are giving me the roll number. Then this, if you are asking me to divide this single entry into parts, it is forcing me to divide this atom. Then this table will not be in first normal form. So if it is asking you to divide, we consider that it is indivisible. But if you are asking them to divide, then it will not be in first normal form. Every entry is atomic. It is not allowed to divide. Now we will see the definition of good database design. The good database, when the relationship is said to be in the good form, you are partitioning the relation R into its decomposition. You need to partition them because whenever you are creating a project or whenever you are creating any application, you cannot keep all the fields in one table because it will make your table very bulky as well as difficult to understand, difficult to process. We have to divide this relation into multiple R1, R2, R3. How this decomposition should be there? This decomposition is said to be the good one when every R1, R2 is in good form, and this decomposition is a lossless decomposition. No information is lost. We have seen the definition of lossless decomposition where R1 intersection R2 tends to either R1 or R2. Now we are slowly moving to the functional dependencies. The functional dependency is one of the form of primary keys or super keys. What is the primary key and super key? In a relation, the primary key and super key will identify your each and every row uniquely. If it is an ID, ID is your primary key, then ID is identifying every row in a table is a unique. But the functional dependency, you can say it is a generalization of a key. It is not the same, but it is some form of this. How it is some form of this? It says that the functional dependence says that the functional dependence says that you have certain set of attribute that define the another set of attributes. What does this mean? This means that if you have the functional dependency A tends to B, the A tends to B says that you have a certain set of attribute that is A, which is going to define B. What does this mean? It says that if in table A, if you have entry of table field A as 1, then if the values are same, then the B value should also be the same. B value should also be the same. If you have a different value of this, then it can be the different one A. Or if you have another entry of 2, it you have A. Means this A is determining the value of B. If the values of a value of two rows of A are same, then the same values should be there in the case of B. 2 is determining 2 means this A is associated with 2, B is associated with 1. It means the A is determining B. In case of the function, in case of the normal key, all the entries were different, but in this case the entries can be the same, but if the entries are same, then the function the value which is functionally dependent on E, it should also be the same. If it is different, then it can be the different one, but for the same values the value of B should be same. Now we will learn its formal definition of 8 alpha tends to beta. Alpha tends to beta, alpha and beta both are the columns of R. When the alpha tends to beta hold, the alpha tends to beta hold means if for any two tuples or any two rows, if the alpha is same, it says that the beta is also going to be the same for these two rows. So we have taken two rows T1 comma T2. If T1 alpha is equal to T2 alpha, then T1 beta should be equal to T2 beta, as we have seen. If T1 alpha is equal to T2 alpha, then T1 beta should be equal to T2 beta. If T1 alpha is equal to T2 alpha, then T1 beta should be equal to T2 beta. Now you have to check if these entries are given. In this entry, whether A tends to B holds or not. This is A and this is B. A tends to B holds or not. A tends to B holds or not if in two tuples T1 alpha is equal to T2 alpha. Here it is expecting that entries 4 and it should also be the 4 1. Yeah, here also it should be the 4 1. If it could have been the 4 1 means 4 1 is associated with 4. Then A tends to beta could hold. But here with 1 it has come 5. So A tends to beta does not hold. It does not hold. With 3 7 it okay with us. In the reverse way also you can check whether B tends to A holds or not. Value of B 4. If all the entries are different, then B, if value of it is 4, it is 1. If it is 4, it is 1. If it is 7, it is 1. All the values of B are different, so we are not bothered about the A values. If they are same, then only we are bothered. If all the entries are different, we are not bothered, means B tends to A holds. So you will be asked in the grade for such type of, you have been given some table and the data, looking at them, you have to find out which functional dependencies hold. So you should learn how to check for the functional dependencies while looking at the data. Now we are defining the super key in terms of functional dependency. How can you define a super key in terms of functional dependencies? So super key or functional super key, K is called to be the super key if K tends to R. R is all the fields A, B, C. So K tends to R means if your table has A, B, and ID. We will take one ID field. If your table has three fields ID, A, B, then ID tends to, if ID tends to IDAB holds. ID tends to IDAB, which is R. If ID tends to IDAB holds, then you can say that ID is a super key. It says that ID is going to uniquely identify each and every row present in table R. Now, how will you define the candidate key? The candidate key can also be defined with help of these functional dependencies. What is the definition? The candidate key is also a super key, but it is a minimal, it is a, you can say it is a minimal set of attributes which identify each and every row. So in this, it is a super key. So first condition holds K tends to R. And in the second condition, no subset of K, no subset of K should also uniquely identify the every row. No subset of K should also uniquely identify the every row. Then alpha tends to R also hold. Then it will be a candidate key. So with the candidate key, you need to check for two. One is a K tends to R, second is alpha. Alpha where no alpha is subset of K. Now we will see this the functional dependency and decomposition. You need to check whether the functional dependencies hold or not. We have been given a relation institute department. In this relation, we have these 1, 2, 3, 4, 5, 6 fields. We have 6 fields. In these 6 fields, we have underlined values which are the keys in some ways. ID and department name. This ID is a key for every row present in this table, but this department name is a key only for these three. It is not for a table. It is only for these three fields. Now we expect that which functional dependency can hold? The functional dependency department name tends to building can hold. Why? How does this hold? If the department name changes, its building will change. But if the department name is same, then its building is going to be the same. Say for example, computer science department is running in the annex building. Whenever the department name CS will come, it will always, building will always be annex 1. If the mechanical department is running in the academic building, then if the department name changes, only then building changes. If the department name is same, building is going to be the same. So this functional dependency hold for our database. The second functional dependency, ID tends to building, will also hold because ID is a primary key or a super key for this every row present in this table. It is going to be the unique one. You can see from the first table, in the table 1, we have seen that this ID is going to be the unique one. It is going to be the different. If every entry is different, every functional dependency hold on ID. And you can see that if department name is same, then building name is also same. Computer science, Taylor. If department name is same, building name is also same. So the department name tends to building holds and ID tends to every field holds. You can take every field. So ID tends to building, we can take every field, ID tends to building hold. But which functional dependency does not hold? The department name tends to salary. The salary is associated with every ID, every employee. And if the department name is same, salary is not going to be the same. In CS, I have 10 faculties. Everyone's salary is going to be the different. So department name is, even if department name is salary same, but salary is going to be different because salary is associated with employees, with the faculties, not with the department. Then this functional dependency does not hold. Now we will see a very important definition of functional dependency, which is a trivial functional dependency. Trivial is, it is obvious. What is obvious? Some things are obvious. The sun rises in the east, or many things are obvious, which are the facts. A student is learning in the college, and whenever it entered to the college, it has been provided some IDs. So some of them are facts. It is going to be, we call it as a trivial information. It is going to be satisfied by everyone. That is a trivial information. So when the functional dependency is going to be the trivial, which says that you need not to see the data, it is going to be true always for every data. So which functional dependencies are called to be the trivial? If you have this in right hand side, whatever field you have, if it is a subset of left hand side, id tends to id tends to id, name tends to name, uh, age tends to age. These functional dependencies are the trivial functional dependencies. If left hand side is same, right hand side is also going to be the same. If some fields which are the keys, which are the super key, which are the keys or the candidate keys, with that, if you combine any other field, if id is identifying each and every row, even though you combine either with the name or with salary or with department, it is going to be uniquely identifying the row, because it is id is identifying the rows. And if you combine it with any other field, it is going to identify your rows. So if with the primary key, if you combine with any other field, it is going to identify it. And if you get this id and id in both sides, it is going to be the trivial functional dependencies. You can also see this, if in right hand side and left hand side one field is common, then it is going to be the trivial functional dependency. So you can see that if beta is subset of alpha, then it is a trivial functional dependency. Now we will see how to find out the closure set. The closure set means some of the functional dependencies are given, but some of the functional dependencies can be derived from the given functional dependencies. Say for example, A tends to B holds and the B tends to C holds, then logically implied that A tends to C holds. So if you find out the closure set, then you have to include the other logical implied functional dependencies as well. So closure set is defined as the closure set is defined as all functional dependencies which are logically implied by F. It is a closure set. The closure set has to be calculated by F plus. If F is a set of functional dependencies, you have to include all the F as well as the functional dependencies which are logically implied. F plus implied functional dependency will make F plus. So F plus is always going to be the superset of F. Now we are starting with the normal form. One of the normal form is BCNF, Boyce Codd normal form. The Boyce Codd normal form is, we have to first define the definition of Boyce Codd normal form. Then we will see how to check whether relationship is in BCNF or not. If it is not, then we will be decomposing this relationship into the multiple relationship so that your relationship has come in BCNF. Now we will first see how to check whether a relationship is in BCNF or not. Every time to check whether relationship is in BCNF or not, you have to first see the set of functional dependencies F. First see the set of functional dependencies F. So you have to see all the functional dependency of type alpha tends to beta. For all functional dependencies, either alpha tends to beta should be the trivial one. Trivial one means obvious. Or either this first condition true or alpha should be the super key. If none of the condition true, then this relationship R is not in BCNF. The relationship R is in BCNF if for all alpha tends to beta, either alpha tends to beta should be the trivial functional dependency or alpha should be the super key of R. Now we need to check this relationship is given. In this relationship, this functional dependency hold. This functional dependency hold. Now you have to check whether this is in BCNF or not. So you have to apply this functional dependency alpha tends to beta. Alpha tends to beta, it is not a trivial functional dependency. So first condition does not hold. This is alpha and this is beta. It is not a trivial functional dependency. No field is common. So it is first condition does not hold for us. One condition does not hold. Now we will check for the second condition. The second condition says alpha is a super key. The second condition is alpha is a super key. What is alpha for us? Department name is alpha for us. Alpha is not a super key of this. Look at this. The super key is ID. The department name is not a super key. So both condition does not hold. So this relationship is not in BCNF. So you will be asked in the gate examination like this. You have to check whether this relationship is in BCNF or not. And you will be given relationship and the applied functional dependencies. How will you check? You have to check like for all alpha tends to beta, either it should be a trivial functional dependency. In our case, it is not a trivial functional dependency. And the second is alpha is a super key of R. In our case, department name is not a super key. So it is not a, it is this relationship is not in BCNF. Now we will divide it into what is the algorithm to convert a relationship into BCNF. To convert a relationship into the BCNF, how will you decompose? You will first create a table which will consist of alpha and beta. First table will consist of alpha union beta, which is in our case, we will see what is alpha, and second will be R minus beta. R minus beta. So our relation will be decomposed into two parts. We are decomposing the R into two parts. The one is R minus beta and second is alpha beta. It is decomposed. Now we will see how it is decomposed. In the previous example, all 5 fields were present. And in these 5 fields, the alpha functional dependency this holds, alpha tends to beta. This R will be decomposed. So this R will be decomposed. Alpha is department name and beta is building comma budget. So first decomposition will be alpha beta, that is department name, building and budget, alpha beta. So your first decomposition will be department name, building and budget. The second decomposition will be from R you have to subtract only beta field. So from R you will have to subtract the budget and building. So you will be getting the 4 fields ID, name, salary and department name. So your two decomposition will become this is R1 and this is R2. You can see that this decomposition is a lossless decomposition. Why it is a lossless decomposition? The department name is common and from department name the functional dependency department tends to building comma budget holds, which says that the common field which is a department name tends to either R1 or R2. In this case it is if it is a R1, so in this case our department name tends to R1. The department name tends to R1. department name tends to R1. So this is our lossless decomposition. Now you need to check whether this relationship has come in BCNF now. You can see that department name tends to building comma budget. That is the department name has become department name has become a super key for R1. So this alpha has become a super key of R1. So this relationship has become a BCNF. With the BCNF, you need to check for the dependency preservation as well. This is again a very important terminology, the dependency preservation. The dependency preservation says that whenever you want to check for any functional dependency, you should be able to check a particular functional dependency only in one relation. It should not be needed to combine the multiple relation to check a functional dependency. We will see in detail. The dependency preservation says that you need to test all the functional dependencies on individual relationship, and it should not be if you can calculate the functional dependency by using only a single relation, either R1 or R2, then you can say that it is dependency preserving. But it is not always the case. Sometimes you may have to combine the multiple relationship to check the dependency, to check the functional dependency. We will see this case. But at this stage we learn that the BCNF does not preserve the dependency. To preserve the dependency, the third normal form has been derived. Because dependency preserving is very important parameter in the case of database design, but the dependency is not preserved in the BCNF. So we go for the another normal form, which is a third normal form. This third normal form overcome the problem of dependency preservation. Third normal form preserve the dependency. It preserve the dependency. Now we will see its definition. What is the definition of third normal form? The third normal form also goes in the same way. You have to calculate the F plus. You have in the BCNF, we have not calculated the F plus, but in case of in case of third normal form, you have to calculate the F plus. What is F plus? F plus is derived functional dependencies. The functional dependencies which are logically implied. So you have to derive them. That is, and you have to combine them all together to get the this closure of functional dependencies. So the third normal form says that alpha tends to beta is the first condition to check the third normal form is that alpha tends to beta should be the trivial functional dependencies, means it is a obvious functional dependency, which says that if beta is subset of alpha. Or the second condition is alpha is a super key of R. These two conditions were applicable to the BCNF as well. Both of the conditions are same. In third normal form, additional condition is added, which is this one. This condition says that you have to find out the fields in beta minus alpha. You have to subtract from beta minus alpha whatever fields are remaining. That field should be the part of a candidate key. If this condition holds, then relationship be in the third normal form. So in BCNF, we checked only for two conditions. In this case, we are checking for three conditions, means we are more relaxed. And the third condition you need to check is the fields in beta minus alpha should be the part of the candidate key. Part of the candidate key means if A comma B is a candidate key, then its part is A or B. So the fields in beta minus alpha should be the part of candidate key. If third condition holds also, then it is in third normal form. This third condition is meant to check the dependency preservation, which was not possible in case of BCNF. So our good definition, the good form of definition now has been changed. It says that every relationship should be in good form. It should be the lossless decomposition. And third is your decomposition should be dependency preserving. The third normal form, preserve the dependency. We will learn how the dependency preserving can be checked. But the third normal form, preserve the dependency, and it is a sign of good database design. Now we are learning with the closure set how to calculate the closure of functional dependencies. To calculate the closure of functional dependencies, we will see which are the other logically implied functional dependencies. If in a set F, if you have A tends to B and B tends to C, then in F plus you will add A tends to C as well. So F plus will consist of A tends to B, B tends to C and A tends to C. So you have to calculate the F plus closure set of functional dependencies, which you need to do for third NF. Now we will see the rule to calculate the closure of functional dependencies. The first rule says that it is a rule of reflexivity. The reflexivity says that if the beta is subset of alpha, then alpha tends to beta holds. We have seen that id tends to id comma name. So in this case, the beta is subset of alpha. This is a rule of reflexivity. Alpha tends to beta hold. The second rule is if alpha tends to beta, you can multiply it by gamma. So alpha gamma tends to alpha beta also holds. It is a rule of augmentation. If alpha tends to beta, beta tends to gamma, then alpha tends to gamma also holds. It is a rule of transitivity. These rules are sound and complete in the sense that they generate all the possible functional dependencies that hold, and they are going to be the true one. They actually hold, and that's why they are derived. Now we will see how to calculate the F plus. This is relation R, and you have been given this set of F. Now, which are the other functional dependencies that can be derived from this? How to calculate the F plus? So we will be using the rule of reflexivity, transitivity, and augmentation. Looking at this, which functional dependency hold? You can see that A tends to B, B tends to H, then A tends to H hold. So the first member can be A tends to H. How it is derived? A tends to B, B tends to H, then A tends to H holds. What are the other functional dependencies which can be derived? You can see that the other functional dependency which can be derived is AG tends to I. How this comes? AG tends to I. You can multiply this with G, AG and CG. AG tends to CG and CG tends to I. Then AG tends to I. So this functional dependency can also be derived. AG tends to CG, CG tends to I, then AG tends to I. In the same way, AG tends to CG, CG tends to H, AG tends to H also holds. The other functional dependency which hold is CG tends to H, CG tends to I, then CG tends to HI. This functional dependency also holds. So you have to calculate like this and find out its closure. So closure will be consisting of all these F plus this, plus this, plus this, and many more. The other additional rules to calculate the F plus is, one is a rule of a union. This rule says that if alpha tends to gamma holds, if alpha tends to beta holds, and alpha tends to gamma holds, you can combine this right hand side, beta gamma. So alpha tends to beta gamma holds. It is a rule of union. The opposite to union is a decomposition. If alpha tends to beta gamma holds, then alpha tends to beta will hold and alpha tends to gamma will also hold. So it is a rule of decomposition which is opposite to the first one. The pseudo transitivity says if alpha tends to beta holds and gamma beta tends to delta holds. You can see that you can match this beta with this. How will you be matching this beta with this? You will be multiplying it with gamma on both sides. So if you multiply with the gamma on the both sides, it is a gamma alpha tends to gamma beta and gamma beta will be replaced with delta. So gamma alpha tends to delta. This gamma alpha and alpha gamma, both of them are same. The order does not matter at all. So these above rules are also called as the Armstrong axioms. So these three are union, decomposition, and pseudo transitivity. Now we will see how can you find out the closure of attribute sets. Till now we have seen the closure of functional dependencies. Now we will see how can you calculate the closure of attribute sets. To calculate the closure of attribute sets, if say for example alpha tends to beta holds, you have to find out alpha plus closure of attribute alpha plus. How will you calculate it? To calculate alpha plus, in our case the alpha tends to beta holds and we are calculating the alpha plus. Alpha plus says that from alpha, which are the other fields can be derived. Here from alpha, you can derive the beta. So alpha plus will consist of alpha beta. So this way you can calculate the alpha plus means which are the other fields which can be derived from alpha. They will come under alpha plus. To calculate the alpha plus, you have to first create a temporary variable of result and it will initialize with alpha. And whatever functional dependency are present in F, you have to process all of them. For each and every functional dependency in F, you have to do this process. Take one by one and do this process. For this process, if alpha tends to beta and alpha is present in the result, then you have to add the beta in the result. If a functional dependency beta tends to gamma holds and beta is already present in the result, means left hand side is already present in the result, you have to add the right hand side as well. And you have to do this for all applicable functional dependencies. Now we take one example. The example is if you want to calculate for a plus. If it is a plus, in the a plus, result will initialize with a. If a is present in the result, a tends to b, left hand side is present in the result, you will include b. So result will become ab. Now we will see the functional dependencies whose left hand side is already present. This a is present here, so a tends to c, c will be added here, a, b, c. Now we will see the other functional dependency whose left hand side is present. CG, the G is not present. CG, the G is not present. B is present, so you can add the H here. So A plus will consist of A, B, C, H. Now we are calculating AG plus. You can have the multiple attribute. Its closure can be calculated AG plus. The method is going to be the same. Result will be initialized with AG. And if left hand side of functional dependency is in result, right hand side will also be included. And then you have to do for all the functional dependencies. So result will be initialized with AG. In AG, you can see that in AG, whose left hand side is AG, the AB left hand side is in AG. So you will add B. AC left hand side is in AG, you will add C. So you can add B and C. Your result will become ABCG. Now which functional dependency can be processed? CG. This functional dependency can also be processed. CG is part of it. So you will add H here. You can add H. Next functional dependency can also be processed. CG is the part. I can also be added. Phi can also be added. Next is B is a part of it, and its H is also a part. No other functional dependency is left. So its result is A, B, C, G, H, I. So that way you can calculate the closure, or you can say closure of any attribute. It can be, they can ask you calculate the CG plus, B plus, H plus. So you should know how to calculate the closure of any attribute. Now you have to check. If you calculate the closure of any attribute, it allow you to check whether AG is a candidate key or not. Such type of questions are also asked in the GATE examination. If such for given set of functional dependencies, you have to calculate the candidate key. How will you calculate the candidate key? To calculate the candidate key, you have to first take sum of the attribute and find out its closure, AG plus. And then if for AG plus, if all the fields in R comes under AG plus, AG plus will consist of all the fields A, B, C, G, H, I, all the fields, then this AG can be a candidate key. If AG derive R means value of AG is a superset of R, means in the AG plus all the fields of R should come, then it will be the candidate key. It will be a super key. Sorry, it will be a super key. If it is a super key, you have to check it is a candidate key or not. A candidate key is a minimal set. So you have to check whether A alone can be A alone can uniquely identify the R, or G alone can uniquely identify the R. So if you see A plus, if A plus consists of all R and G plus also consists of all R, then A can be a candidate key, G can be a candidate key, but combination will not be a candidate key, it will be a super key. So the calculation of closure, attribute closure, will help us to test for a super key. We have seen you have to calculate AG plus, and then if AG plus has R, then it will be a super key. You can also test whether the functional dependencies hold or not. If you have been given this alpha plus, in the alpha plus, and you will be asked whether this alpha tends to beta hold or not. How will you check? If in alpha plus the value of beta is coming, means alpha tends to beta hold. So you can check whether alpha tends to beta holds or not by looking at alpha plus. Now we will check for the canonical cover. The canonical cover is, the canonical cover is used in the fourth normal form. The canonical cover questions are asked in the canonical cover as well. The canonical cover will tell us the minimal set of functional dependencies. What is the minimal set of functional dependencies? In our case, we have seen that A tends to B, B tends to C, and A tends to C as well. But if the A tends to B and B tends to C, it is obvious that it is going to be A tends to C. You need not to add A tends to C. It is a duplicate information that you have added in this functional dependency set. So you have to remove such type of obvious functional dependencies which is not which should not be given in the set, which are obvious one. It is going to hold. You need not to create the duplicate functional dependencies or duplicate attributes in the set. So minimal set of functional dependency is called as a canonical cover. How to calculate the minimal set of functional dependencies? We will see some of the examples as, if A tends to B, B tends to C, we can divide it as A tends to C and A tends to D. How this can be divided? It can be A tends to C and A tends to D. A tends to D. But you can see that A tends to B and B tends to C hold. It is not required to keep the A tends to C now. So you can remove it. So you can simplify it as a tends to D. So the information which is required to be kept need to be kept, but the additional information should be should be removed. That is a canonical cover. You can, so in the same way you can you can remove from the left hand side as well. How can you remove? If A can determine B, B can determine C, uh, uh, if A can determine B and B can determine C, you can remove this C is a extra attribute. You can remove it, and if you have removed this C attribute, it is representing the same information. How this extraneous information is removed, we will see later on. So now we are taking one example to calculate the minimal cover or a canonical cover. How to calculate the minimal cover and canonical cover? To calculate the minimal cover and canonical cover, you need to first remove all the extraneous attributes, and then you have to remove all the redundant functional dependencies. To do this, the first step is that you have to apply the split rule. What is the split rule? The split rule says that in right hand side, if you have the multiple attribute, you have to split them. I need a single attribute on right hand side. So you can divide, you can use the decomposition rule, and you can do it by adding two functional dependency, which is A tends to B and A tends to C. So you have to split them. In right hand side, if you have multiple fields, split them. A tends to B and A tends to C. But in left hand side, we are not processing at this step. In the first step, you are processing only the right hand side and splitting them. In the second step, we will be removing the extra attribute. And the third step, we will be removing the functional dependencies. So it will consist of three steps. One is splitting rule. We have seen the splitting rule. And now we will see how to remove the extraneous attribute and remove the functional dependencies. Now we see that how to see the extraneous attribute. How to see the extraneous attribute? If you have two functional dependencies present in the set, AB tends to C and A tends to C. If A can alone do the task of C, A can alone determine the value of C, the B is not required. So you can remove it. A can alone uniquely identifying the C. So it is not required the B to be here. So you can remove the B entry. So B is an extra attribute. You can remove it. So how to check, how to calculate the extraneous attribute? To calculate the extraneous attribute, we will find the extraneous attribute only on the left hand side, because in the right hand side we have converted into single entry. So we can get the extraneous attribute only on the left hand side. How can you check whether it is an extra attribute? It says that if you remove A from alpha, if you remove A from alpha, after removing it, it has become alpha minus A, and it should also if alpha minus A tends to beta and alpha tends to beta, both are together, both are the logically implied them, then you can remove the you can remove from remove A from alpha. We take one more example to see how can you remove the extraneous attribute. We have seen that if AB tends to C and A can alone determine the C, the B is not required. If A tends to B has been given, A is determining B and AB is also determining C, the B is again an extraneous attribute. It is not required. So either this holds or this holds. If A tends to B holds, you can remove either A or B. Any one can be removed. So remaining functional dependency will be either A tends to C or B tends to C. So that way, every student will get the different answer. If you see to A tends to B and one can remove for B, one can remove A also. So it depends on you, but you have to remove some information. Now look at this. If AB tends to B, AB tends to C, and B tends to C already hold. If B can determine C, the A is not required. Or if B tends to A, means you can remove A or B, either of them. So you can remove A and then you can get B tends to C. So that way you can remove the extraneous attribute. And now in the next step, we are not processing BA tends to C. We are not sorry, this AB tends to C is same as that of BA tends to C. It doesn't matter it is AB tends to C or BA tends to C. Now we take one example. You have to find the canonical cover for this example. This example has been given. You have to find the minimal set of functional dependencies which are present and remove all the extra functional dependency, remove all the extra attribute from this. How will you process it? You will apply the first step, and on the first step you have to see all the functional dependencies which has right hand side more than one, which has right hand side more than one, and we will apply the decomposition. So C tends to AB will be decomposed into C tends to A, C tends to B, and ABC tends to AC will be decomposed into ABC tends to A and ABC tends to C. And rest of the functional dependency you can take from the above. The rest of the functional dependencies take as it is. B tends to C, take as it is. A tends to C, take as it is. AC tends to B, take as it is. After this step, you have to note down that on right hand side, you will always get a single attribute. All So after this step, you have to see the trivial functional dependencies. You can see that a trivial functional dependencies are whose right hand side is also present in left hand side, then it is a trivial functional dependency. So A is present, it is a trivial functional dependency. C is present, it is a trivial functional dependency. Remove them. A tends to A, B tends to B. There is no sense to keep. Remove them. So these two functional dependencies will be removed. Now you are left with these one. AB tends to C, C tends to A, C tends to B, B tends to C, then A tends to C, and AC tends to B. Now after removing them, you have to see this AB tends to C and AB tends to C, and you can see the B tends to C. These looking at these two functional dependency, if B can alone determine the C, it is not required to keep A. Remove the A. So B tends to C will be left. The other student can see A tends to C. If A can determine C, B is not required. The other student will remove B. So every student will get the different combination. So I am going for B tends to C. So I am removing A and I am left with B tends to C. Or it can be A tends to C as well. Now we will see AC tends to B. In the AC tends to B, you can see that A tends to C. So you can either remove A or C from it. So you are left with either A tends to B or C tends to B. You can remove, you can be left with A tends to B. So you can remove C. So now you are left with B tends to C, C tends to A, C tends to B. In this, all the functional dependencies, left hand sides are single attribute and right hand side are also single attribute. This is a question like this, but you can get the multiple attribute on left hand side, but on right hand side you will get the single attribute at this stage. So in the right hand side you have only single attribute. Now we are left with the third step. This third step says that you have to remove the redundant functional dependencies. How can you remove the redundant functional dependencies? You have to calculate the closure of attributes. To calculate the closure of attributes, you can see that this B tends to C has come 2 times. So you can remove it. B tends to C, it is not required. So we will move ahead with 1, 2, 3, 4, 5. Now we will calculate, we will process this functional dependencies. To process this first functional dependency, you have to hide it and calculate the value of C plus. How to hide it? You can hide like this and calculate the value of C plus. What is the value of C plus? C is deriving B and B is deriving C. So C plus will consist of CB. You have to hide it and C plus will consist of CB. Now you have to, what you have hidden? You have hidden C tends to B. If in C tends to B, in CB, C tends to B, the B has become a part of it, then you can remove it. You can remove, if it has become a part of it, if it has become a part of, the right hand side has become a part of it, then you can remove it. Otherwise, you cannot remove. So you were hiding, what you were hiding? You were hiding C tends to A, but the A is not a part of it. A is not a part of it. So you cannot remove it. So A is not a part of it, you cannot remove it. Now we will process the second one. What is the second one we are processing now? C tends to B. C tends to B means you have to hide C tends to B. We are processing now C tends to B. We have hidden. Now, whatever you have remaining, you have to calculate the value of C plus now. The value of C plus, why you need to calculate again and again? Because you are hiding the different information and displaying the different ones. So you need to calculate them again and again. The C plus will consist of CA, then AC, then AB, then it will consist of CAB. CAB, the B part is present in the right hand side, so you can remove it. So you can remove it. Now we are processing the third one, B tends to C. In the B tends to C, you have to hide B tends to C. You have to hide B tends to C. B tends to C. Now calculate the B plus. While calculating the B plus, you will be processing only the information which is left. The crossed information will not be processed. Hidden information will not be processed. What is the value of B plus? B plus will consist of B only because no functional dependency is participating in B plus. So B plus will consist of B only. This right hand side is not the part of B. So this functional dependency will not be removed. So you have to do this again and you have to do this for the next one. And you have to do like again and again. After doing all this processing, you have to remove the functional dependencies whose right hand side is present in its closure, or if it is not present, you have to keep it as it is. After doing all this processing, you will be left with the answer of C tends to A, B tends to C, and A tends to B. It is a canonical cover of this functional dependency. You can see that how much information was present, and they are representing only this information. This is a minimal set of information. All of them were extra attributes and the extra functional dependencies. So this is how to calculate the canonical cover. That is it for today. We will continue in the next class.